Okay, onto this spring lab design question. I really liked this one. This was a really good typical lab design question. This is very in the range of things I've done in class. Uh, Very typical. So, a student hangs a spring of unknown spring constant K vertically by attaching one end to the stand. In addition to the spring, the student only has access to a variety of cylinders of unknown masses, a stopwatch, and a digital scale. So, what's important here is that for springs, the easiest way is to take a spring, measure its length, attach a mass to it, measure its change in length. K equals mg over delta x. Boom. Unfortunately, we do not have a meter stick. So, we have to do this without measuring lengths. So, that is important. Unfortunately, you could not do anything with meter sticks. So, maybe we should explicitly write no meter stick. But that's actually not a problem. There's a nice time oscillation approach to this as well. So, really what we're going to do is uh some sort of the period of oscillation. So I guess I'll draw my diagram first and then we'll talk about it. So the classic thing to do here will be to hang each mass from the spring, and then we displace it a bit. And what we're going to do is, obviously, if it's at equilibrium and we displace it, it's going to bounce up and down, up and down, up and down, oscillate. What we want to measure is, I'm going to say the 10 periods of oscillation. So this is one way to reduce uncertainty. If you just said the period, I'm sure that's fine. This is just one of my ways of reducing experimental uncertainty. So I'm going to call this T10 because measuring one period could be tricky. So I'm going to measure 10 of them. And then after that, we can measure the mass of each cylinder. And that's just going to be M. So we just do that. We time 10 oscillations. So period is going to be equal to T. So time 10 oscillations, T10. So the procedure is just going to be measure mass M, time 10 periods to reduce timing uncertainty. Then T is going to be equal to T10 divided by 10. Then repeat for all cylinders to reduce uncertainty. So now you have data for M and T. And I believe we just want the procedure, describe the overall procedure there. And then we're going to talk about how to analyze the data. So the reason we're graphing M and T, again, we have to have an equation here. So If we look at our equation sheet, the time of a mass spring oscillator is 2 pi square root m over k. And square roots aren't the best to deal with. So typically we suggest squaring both sides. So t squared would be equal to 4 pi squared divided by divided by k times m. So m is a variable and t is a variable. So now this is y equals mx plus b format. So we would graph t squared as a function of m, because the slope of our graph would be equal to 4 pi squared divided by k. So then after doing some algebra, you can get that k is just going to be 4 pi squared divided by the slope. This is not the only solution. You could have graphed, let's just run through them. T versus square root m, slope would be 2 pi over square root k. You could have graphed reciprocal versions of this, m versus t squared with slope k divided by 4 pi squared. You could put constants in here to make things easier. So many solutions. It just has to somehow be derived from this expression. The t is 2 pi square root m over k. And if you have any questions on if a linearization is suitable, you can ask and we'll sort it out. But this is a very classic get the spring constant without a meter stick experiment. So again, you just create a mass spring oscillator, you time it. I pick 10 times and then take an average just to reduce uncertainty. Repeat for all cylinders to get a full data set. And then you end just by graphing t squared versus m. Should be some sort of a straight line. And the slope is 4 pi squared divided by k. And now, just because we got to complete the question, I guess, here's just some random oscillation stuff. So they got a cart attached to the spring, and then it's just oscillating back and forth. We got V of t and F of t graphs. Using the data from the velocity graph, calculate the change in kinetic energy between 0.5 and 0.2. Well, delta k explicitly is just going to be k at 2 minus k at 0.5, which is equal to 1/2 mv squared at 2 minus 1/2 mv squared at 0.5. And we're given the mass is 0.25, so we can factor out a 1/2 and factor out the 0.25. That's the mass. And then we can just look at our graph and look at our v's at each time. So v at 2 is 0, and v at 0.5 is 0.3. So we get 0 squared minus 0.3 squared. And that is going to be, let's see, 0.125 times 0.9. Calculate this here. Negative 0.001125 joules. Lovely. So let's check, quick sanity check. I got a negative number. Well, I started with velocity, I ended without velocity. So yeah, that's a negative change in k. Then, using data in the force time graph, estimate the change in momentum in the cart. So force time. So we can't just use the delta v's. That's part 3. Well, we know that delta p is equal to the area bounded by ft. So let's see. Since it's estimated an area, it's either something we can get by counting boxes, or it's obviously 0. Let's see which case we get, because they're probably not going to make us really count boxes. So hopefully we got some symmetry here. 0.5 to 0.25. And oh look, it's symmetric. Thank you, College Board. Thank you, College Board. So we have a negative change in momentum for the first second. And we have a positive change in momentum for the second. And notice those are pretty clearly symmetric, so they're going to cancel out. So, since the graph, since the area is bounded by the graph, are approximately equal and opposite, delta P is roughly equal to 0. So, to get points on this part, I'd imagine you'd have to obviously reference delta P is going to be roughly 0, and then something like this, indicating that you have some knowledge of the fact that these two areas are going to cancel. And I imagine they're pretty lenient with what that means. Do the data from the velocity time graph confirm your estimation? Well, this is even easier using impulse momentum theorem. So impulse is obviously the force time area, but more explicitly, it's just m times delta v. So our mass is still 0.25 kilograms. And if we're estimating the change in momentum between 2.5 seconds and 0.5 seconds, we can just take the v's at each of those times. So let's see what we get. Well, v of 0.5 is 0. Oh, let's use blue. I haven't used that yet on this graph. V of 0.5 is 0. V of 2.5 is 0. 0 minus 0 equals 0. So we see that we get the same answer. So does the data tell us, does it agree? Yes. This confirms the estimation. Some sort of semblance of the word yes. Again, this math is proof enough. Briefly explain, I mean, delta V is 0, so impulse is 0. If you mathematically did it, it's proof enough. Okay, and that's it. So let's do the point breakdown now. So what are we adding up to? We're adding up to 12. Okay. Okay, let's see. How are we going to get to 12? I imagine that this procedure writing, since it's pretty basic, I'm not totally sure, but I would guess maybe this is just 3. So you probably get a point just for identifying what to do measurement-wise. You probably get a point for some sort of understanding that this is oscillation-based, and then some sort of uncertainty point. This could very easily be 4 as well. I'm not sure, though. For this one, this is the one that could go either way. This is also 2 or 3. I'm going to think this is 3. Indicate the quantities that could be graphed. So you get a point for identifying a valid linearization. And then I bet you get 1 point for explaining that you know that the relationship between T and M is this formula. And then you get another point by coming up with some sort of a K expression in terms of the slope. So that gets us to 6. And then these are 2 apiece. So get a point for identifying what delta K is, then you get a point by doing it. Get a point for identifying what delta P is, get a point by doing it. Get a point for identifying the other version of delta P and showing that it's consistent/inconsistent with the other answer. So I think that's pretty typical. Very non-terrible lab question this year. I thought this was pretty achievable.